Okay, we're on page 124 of the note spiral, looking at scenario 3. And I'm going to use the type notes so I can speed through this because this is the third one. So insurance companies track life expectancy information to assist in determining the cost of life insurance policy. The insurance company knows that last year the life expectancy of its policyholders was 77 years. They want to know if their clients this year have a longer life expectancy on average. So the company randomly samples some of the recently paid policies to see if the mean life expectancy has increased. The insurance company will only change their premium structure if there's evidence that the people who buy their policies are living longer than before. Does this sample indicate that the insurance company should change its premiums because life expectancy is now different? Calculate a 90% confidence interval and interpret the level. All right, so first thing, we always have to define, make sure you're looking at your recipe, but we always have to define the parameter. So let mu equal the true population mean of policyholders' life expectancy in years. I'd probably shorten that down, true population mean life expectancy. All right. Conditions, random sample. They told us that it was randomly selected, so we're good to go. We need to make sure that N is less than 10%. So we have 20 policyholders, 20 divided by 0.1 equals 200. And it's reasonable to assume that the company has more than 200 policyholders. Therefore, N is less than 10% of the population. All right. The next thing is our test for normality. And remember, if they tell us it's normal, we're good to go. Well, when I read through this, they didn't tell me it was normal. Well, then I can say it's normal by central limit theorem if my sample size is 30 or larger. In this case, it's not. So because it's not 30 or larger, and they didn't tell me it's normal, I'm going to have to input this data and do a box plot. So I went ahead and I input that data into stat edit. All right, so there's my data all listed in. I'm going to see if I can darken this just a bit so it shows up a little better. I don't know if that helped or not. Hopefully it helped a little bit. So there's the data that I input, and I'm going to go to y equals. Make sure the y equals is blank. You want everything cleared out of that. Then I'm going to go press second, followed by stat plot, enter. Arrow to the left and press enter to make sure it's turned on. Then I'm going to select the stat plot, the box plot showing outliers or dots. All right, those are the outliers. Press enter. My data is in L1, so second followed by the number 1. My frequency should also be 1. If for some reason it's flashing a letter, etc., press alpha followed by 1, and that should take care of it. You may have to do a couple of iterations, but you need to make sure that the frequency is shown as 1. Then we're going to press zoom followed by the number 9. And there we end up with our box plot. Now, I will be honest with you, that's not perfectly symmetric, but it's symmetric enough. All right. And we remember we can use the trace feature to actually get those values to help us draw it. So when I draw this thing, I get a box plot that looks something like that. And so it's reasonably selected, symmetric, with no outliers. So the distribution appears to be normal enough, or we like to say approximately normal. Please use those words. Approximately normal is a really important phrase. Okay, so now that we've done that, we need to go ahead and write our formula and write down our data. And we have 78.6. Like, well, where did that come from? So here's what I did. I went stat calc. I'll slow that down. Stat, then calc, one variable statistics. I pressed enter. Second 1. And 78.6, and my standard deviation of the sample is 4.47. Make sure you're choosing a sample because we're using sample data. So I wrote that down. Now we are making a confidence interval, so this means my graph is going to look like this, where this is 0.90, and I'm looking for this lower bound and this upper bound. and 1 minus 0.90 equals 0.05. So my area in my tail, excuse me, equals 0.10. So the area in my tails is 0.10. So this has an alpha level of 0.10, half of which is here. So this one's going to be 0.05, and this one will be 0.05 as well. Okay, but the alpha level is 0.10. So we have x bar plus or minus t star s divided by the square root of n. Well, we know n is 20, so the only thing we're missing is t star. So we're going to go calculate t star, second vars, inverse t, area 1 minus 0.90 divided by 2. And our degrees of freedom is going to be 20 minus 1, or just plain old 19. And we end up getting a t star of negative 1.7291. So my t star is negative 1.7291. So I'm going to plug all of that into my equation. I always like to keep my t stars positive. Technically, you don't have to, it just makes things easier. So this 78.6 plus a t star, there's my standard deviation of my sample, everything's plugged in. Then I'm going to go stat test, and I'm going to drop down to number 8, which is t interval. Now we're using data, so if stats was highlighted, arrow over to data, make sure that's highlighted. I put my work into L1, so second 1, and my confidence level is 0.90. And so I end up getting an interval of 76.89 and 80.331, and I just write that down. So now we need to write our conclusion. Our conclusion was we are 90% confident that the true population mean life expectancy for policyholders lies within this interval. It also asks us to interpret the level. That means interpret the confidence level. And by the way, if you do this, you have to do every single time. You always have to interpret the interval. This is not required unless they ask for it. Some people just write it down every time as well. Nothing wrong with that. And all this is our brag, okay? And it's in repeated sampling. We expect that this method will capture the true population life expectancy 90% of the time. In other words, if we did this over and over and over again, technically an infinite number of times, 90% of the time it would work, all right? That also means 10% of the time it fails, all right? So we like to say in repeated sampling, we expect this method will capture the true population mean life expectancy of policyholders 90% of the time. All right, and that will conclude the one sample confidence intervals.